Okay, bad videos continue here. Again, as simple as possible, as soon as possible, anatomy and physiology. Just trying to get some good general ideas in front of you to prompt your memory. This is not a replacement for the textbook or the general practice questions or for coming to class or for working with other people, but it may be good for prompting your memory. Here we go. Last time we were together, we talked about anatomy and physiology. We looked at examples of anatomy, examples of physiology. Now let's talk about levels of organization of living things. When it comes to levels of organization of living things, there's a silly way to remember this thing. Some students came up with this once upon a time, and it's called SMOCTSO, and it stands for subatomic, atomic, molecular, macromolecular, organelle, cell, tissue, organ, system, and organism. And trying to keep up with what is bigger than what's smaller than what. This thing right here is pretty useful. It's a mnemonic that I think is very clever. And here we go. When it comes around to the first thing there, the S for SMOCTSO stands for subatomic particles. And there are protons, neutrons, and electrons. The general subatomic particles. We're not going to be going into bosons and quarks and things like that. Protons tend to be positively charged. They're relatively massive. Neutrons do not have an electric charge, but they are still massive. And electrons have a negative charge, and they have barely any mass whatsoever. In fact, by comparison, a proton is about 2,000 times more massive than an electron is. So you have the positively charged protons, the negatively charged electrons. You have the massive neutrons, but no charge to them. The protons and neutrons tend to be found inside the nucleus of a cell, and the electrons tend to be found around the outside. And it's the attractive force between the positive protons and the negative electrons that holds the orbits to the nucleus. So for subatomic particles, protons, neutrons, electrons, know the charges, know their relative mass, know their location. Next step up is atom. A cute little word. A means not, to means cut. So it literally means indivisible. And of course, that's a mistake. Of course, they're divisible now, but originally they thought they couldn't be broken down to anything smaller. When it comes around to the atoms, we identify the different types of atoms as elements. And there's approximately 92 natural elements, and then several more that have been created in the laboratories and such. Now, the simplest of the elements is hydrogen. Hydrogen has one proton in its nucleus and one electron in its one orbit. There's a whole lot of information to learn about how elements are put together and why elements have a certain chemistry. It goes along with what's going on in the outermost level of their electrons. Please remember also that these electrons are moving around constantly, and not just in a flat plane, but they're moving around, forming a sphere around the nucleus. So each atom, if you could see an atom, would look like a bubble, and the outer edge is a spinning electron or a group of spinning electrons creating a kind of a negative skin on the outside edge. Now when it comes around to atoms and elements, there are approximately 12 or 13 most important elements to living things, depending on which book you read. And an easy way to remember this is the expression, C. Hopkins Cafe, mighty good with salt, in which you have C for carbon and H for hydrogen and O for oxygen, and then P for phosphorus, K for potassium, I for iodine, N for nitrogen, S for sulfur, calcium is Ca, Fe is iron, and Na for sodium, and Cl for chlorine. I hope I remembered everything there. Some books don't include iodine as one of the 13 most important elements living things, but it is extremely important. We'll talk about thyroid hormones, T3 and T4, later on. Anywho, so there you get it. The 13 most important elements to living things. They are different types of atoms. So much more to be said. But then if you put atoms together in just the right way, you can create molecules and compounds and such. And a molecule, by general definition, is two or more atoms that are chemically bonded together. There's two types of chemical bonds that we say create compounds or molecules. The weaker one is called an ionic bond, and it's between a positively charged particle and a negatively charged particle. The stronger bond is a covalent bond, and in this one, outer electrons and the outer orbits of two atoms actually are shared between the two atoms. And the end result is you kind of blend the outer edge of the atoms together. So a covalent bond is very, very strong. We have a list in chapter 2 and 3 of the minimum list of the different types of molecules that you really, really need to know for the sake of 2401 and 2402. And it's things such as water, H2O, CO2, carbon dioxide, C6H12O6, glucose, and a few more. Next, if you take molecules and put them together, it's possible to create a macromolecule. And macromolecules are usually so large that you don't really write down their formula. Instead, you just describe them. So DNA, deoxyribonucleic acid, or RNA. Most proteins are macromolecules. Many of the lipids are macromolecules, such as phospholipids. A polysaccharide, starch, or glycogen is also an example of a macromolecule. Well, if you put macromolecules together in just the right kind of way, you can come up with organelles. And organelles, by definition, are the small organs inside of a cell. Now, we'll just jump up here real quick and say that a cell is the simplest living thing there is. And in general, we say a cell tends to have a nucleus, a cytoplasm, and a cell membrane. And when we get around to chapter 4, we'll be much more detailed about that. But consider that inside this cell membrane, inside this bounded area right here, there are structures. And some of them are very easy to recognize, such as the nucleus and the mitochondria. But then there's Golgi, endoplasmic reticulum, different types of vesicles, including lysosomes, Golgi apparatus, if I haven't said it already. But anyway, a lot of different structures we'll be talking about in chapter 4. Next level up is the cell, and the cell is the simplest unit of life. It is the unit of life. Nothing simpler than a cell is alive. So all these components down here are non-living. The cell is the first thing that is living. So the cell. Cells are put together in just the right kind of way with other cells and cell products to make tissues. And the tissues, the four fundamental tissues represented here by E, C, M, and N, will be epithelial, connective, muscular, and nervous. And in chapter 5, we'll go into great detail about some of the characteristics of the epithelial and the connective, and in later chapters about the muscle and the nerve. So think of it this way, a cell is sort of like a brick, a tissue is sort of like a brick wall. By the way, a brick wall is not just made up of bricks, it's made up of mortar and other materials too. So a tissue is made up of cells and cell products. Well, put tissues together just the right kind of way and you can come up with organs. And so, for example, we can talk about the mouth, the pharynx, the esophagus, the stomach, small intestine, large intestine. Each one of those organs right there is made up of coverings and linings of epithelium, holding it together with connective tissue, making it move with muscular tissue, and helping communicate and coordinate activities through nervous tissue. So an individual organ, such as the stomach, is a combination of tissues. But then the organs together working make up a system, in this case the digestive system. For the cardiovascular system, you have the heart, the arteries, the capillaries, the veins. For something like the nervous system, you have the brain, the spinal cord, the nerves, the ganglia, the receptors and such. And again, we've said that inside this chapter, there's about 11 or 12 systems that have been identified. Next thing, as one step up, is the organism itself, you, the whole you, with everything put together in just the right kind of way. Now, stepping back a little bit, please remember that to understand how this thing works right here, you have to understand all these different phases right here. So understanding health, understanding why the body does what it does, means taking into thought all these things right here, even down to the subatomic level, because protons define what acids are. Electrons define what bases are, and it also helps define things like electricity. So yeah, you have to understand protons, neutrons, and electrons to understand what's going on all the way up to here. So even though you may think this is what you're going to be working with in a health situation, you have to know all this to be able to figure out what that thing is doing right there. Good place to stop.